All right, AP Chemistry, folks, this is going to be Unit 5, and it's going to be on electron configuration, quantum mechanical model of the atom, and then periodic trends. So let's see if we can buzz through this pretty quickly here. These are the different objectives we're going to be looking at. All right, starting with objective number 1, the dual wave particle nature of stuff in general. We're going to start with light, because that's the first thing that we know will have both light and wave properties. And so we separate this into the two different categories. This is how we know that it's a wave, and this is the evidence we use in order to explain that it is a particle. So the double slit experiment is going to be that monochromatic light experiment where that light is shown through a material that has two slits, and then on the other side there's going to be some kind of detector that will show what happens to that light as it passes through those slits. And as it passes through, it doesn't show two bright areas like you would see if you were to have like a table here, a hole in it. And then if we poured some kind of a sand or something down here, so here are some oh, and then down there somewhere, we would see then just the stuff pile up here into a pile. That's what we would see if it was a particle. We would just see these two bright spots on the other side of the double slits. Instead, we see this interference pattern. We have places of bright light and places of no light. And so we have constructive and destructive interference, and this is something that you would see with waves. All right, the photoelectric effect on the other hand, though, shows that it has particle properties. So if we shine light on a metal surface, we can show that electrons jump from that surface to a detector. Now, the amount of electrons that transfer would be dependent on the intensity if light was a wave. But we found, the scientists found that the electrons that are transferred here, the amount of them and their energy is dependent on the frequency. And that is what we would see if it's a particle. And so that's the important part there. All right. How does it prove? So that's how it proves it has physical properties. It's dependent on frequency, not the intensity of light. So frequency is the deciding factor, not the intensity. And that's evidence of particles, not of the intensity. All right. Now we can do some of the math problems here. I'm gonna buzz through these pretty quickly here, guys, because most of them are pretty simple. There's a couple here and there that need a little bit extra explanation, but for the most part, it's just a matter of using this equation, or this equation. Kinetic energy plus work. And then it's just plug and chug, making sure you're in the right units. So those are the three equations you had to choose from, and just decide accordingly. So the first one is we're going to use the speed of light equation here. So we're going to get rid of all that. And we end up with then C equals wavelength times frequency. And we plug stuff in. So here, guys, to speed things up, C is equal to 3.0 times 10 to the 8th meters per second. H is equal to 6.63 times 10 minus 34th joule seconds. Those are the two constants that I'm going to be using here quite a bit. And so rather than write out the entire value each time I do one of these problems, I'll leave it as the variable. So in this case, we would have C divided by 8.6 times 10 to the 13th. And that gets us a wavelength of 3.5 times 10 to the minus 6th meters. Need it nanometers. I'll show you this math just once. 1 times 10 to the 9th nanometers is 1 meter. That gets us 3,500 nanometers. All right. What is the frequency with the wavelength here? First thing we have to do is convert this into meters. See, I showed you once going this direction. Let me show you once going the other direction. 566 nanometers. 1 times 10 to the 9th nanometers is 1 meter. And that equals 5.66 times 10 to the minus 7th meters. Now we're looking for frequency in this case. We have to use meters because of the speed of light has the units meters per second. All right, so there's that. C divided by 5.66 times 10 to the minus 7th gets us a frequency of 5.3 times 10 to the 14th per seconds, or we could label this as hertz. All right. Number 11, we have this radiation. Oh, they had to give us an entire thing, didn't they? So that's pretty annoying, the entire value there. So it's the same kind of problem though. We still do C is equal to wavelength times frequency. So we like C divided by that frequency. It's a frequency because we see that cycles. That means number of waves per second. So we have 9,1,9,2,6,3,1,7,7,0 gets us wavelength. Gets us 3.26 times 10 to the minus second meters, or 3.26 times 10 to the 7th nanometers. And this is microwave radiation. So microwave light. All right. Looking at the wavelength of blue light, this is what is caused by the sky refracting certain colors of light, or scattering, refracting. And so we end up with a frequency here. So C divided by 7.5 times 10 to the 14th is equal to 4.00 times 10 to the minus 7th meters, or 400 nanometers. So there's that. Calculate the energy. Here's the other equation we said we would be using quite a bit here. Okay. So the energy is going to be equal to Planck's constant. I'm going to write it out over here. Again, H is equal to 6.63 times 10 to the minus 34th. And that is joule times second. So we have H times V. Frequency is going to be what we had up here, 7.5 times 10 to the 14th. The energy is going to be 5.0 times 10 minus 19th joules. That's a 14, and that is a 19. There you go. All right. Number 17 is essentially the same thing as 15, so I am not going to go through all of the work on this one. Instead, I am just going to give you the answers. This guy is going to have a wavelength of 5.0 times 10 to the 3rd meters, or if we want to convert this into nanometers, times 10 to the 12th nanometers, and this is radio. So this is no. The energy is the same thing here. Let's go ahead and do this because it's just the second time we've seen it. H times the frequency. So energy is equal to the Planck's constant times 6.0 times 10 to the 4th hertz. The energy is going to be a super small number, 4.29 times 10 to the minus 29th joules. Letter C is an interesting problem here, and I'm glad it's fit on the same page for us so we can look at it together. It says calculate the energy in joules of 1 mole of photons. Now this will often throw young chemists like yourselves off because we forget for whatever reason that 1 mole of anything is this number of them. Now we haven't really used this number for several chapters and rarely use it, but that's where it comes up, and it doesn't matter what it is, it's that number. So 1 mole of photons. So this is going to be of 1 photon. So if we take our 4.29 times 10 minus 29th joules, and that is per photon. Then we have 6.022 times 10 to the 23rd photons per 1 mole of them. So we end up with that many joules per photon. It comes out to be 2.4 times 10 minus 5th joules per mole. Easy peasy. All right. Let's see. Yours is in the right order. Mine is not. So I have to go back to question number 15 here. Sorry if that messes with you a little bit. But number 15 is kind of a nice problem because it combines different things together. We first have our wavelength, but we're looking for energy. If we look at our energy equation, again over here, it doesn't have wavelength in it, but this does. And they both have frequency, so I can use the first one. 6.24 times 10 to the minus 7th. Got to get that thing in the meters, guys. I don't know why I just did that. Equals our frequency of 4.8 times 10 14th per seconds. Now I can plug that into energy is equal to Planck's constant times 4.8 times 10 to the 14th. Gets us 3.19 times 10 to the minus 19th joules. And that's our answer there. All right, number 16 here on mine is not on yours. It's a repeat. We already did that one. So let's go ahead and scoot ahead to number 18. This one is fairly involved. So let's go through this guy together. It says, what is the wavelength in nanometers of radiation that has an energy content of this? And where do we find that? We go to figure, by the way, figure 7.4 is the figure you go to find where it is on the electromagnetic spectrum. Now the big thing here is that it's per mole. And so we need to get it out of moles. We also have to get it out of joules. So we have 1.0 times 10 to the third kilojoules per 1 mole. 1 mole is equal to 6.022 times 10 to the 23rd. Because those equations that we look at, the energy equation, that's just for 1 photon of light. So there's 6, that's how many photons there are in a mole. And we're going to put that down here. Photons. Moles cancel. So we end up with 1.7 times 10 to the negative 18th joules. Notice the unit change into joules. That's joules per photon, which allows us to do energy equals Planck's constant times frequency. I know energy is 1.7 times 10 to the minus 18th. Now we need it in joules because Planck's constant is in joules. Remember that Planck's constant is equal to 6.63 times 10 minus 34th joule seconds. So there's Planck's constant, and then we have a frequency equal to, boy, that frequency symbol gets worse and worse, frequency equal to 2.56 times 10 to the 15th hertz. Notice I'm using a different label there. They're the same thing. Wavelength, then we can do this. And the wavelength comes out to be 1.2 times 10 to the minus 7th meters, and that is 120 nanometers. And on my answer key, I forgot to look this up. I think it's going to be UV. I am not sure. So, you should check that. All right. '21. Now we get into the work function questions. I like these here because this requires us to think a little bit about what that minimum means. It says minimum frequency of light needed to eject that electron from the metal. We have this equation, which we brought up earlier. Ooh. There it goes. This here, HB is equal to the kinetic energy plus the work function. And remember that the work function is the minimum amount of energy required to release or to remove the electron from the surface of the metal. So in that case, if we're looking for the minimum frequency here, we're going to plug in, I believe, yes, 0 for Ke. So Ke is 0 because that's what the minimum value for the electron could be. Now, of course, we can't have 0. It'd be something just above 0, but 0 gives us the very minimum. So any number above this value is going to eject that metal or that electron off the metal of the surface of the metal. So we have Planck's constant times frequency is what we're after. And that gets us our kinetic energy, which is 0 plus our 3.68 times 10 to the minus 19th joules, and frequency is equal to 5.55 times 10 to the 14th hertz. Now we have the same metal here, potassium. It says calculate the kinetic energy of the ejected electrons when the frequency of the light is this. So it's a value that is greater than the minimum, and so it's going to have some kind of a kinetic energy. So we have, again, Planck's constant times 8.62 times 10^14 is equal to kinetic energy plus the work function, 3.68 times 10 to the minus 19th. We have kinetic energy is equal to 2.04 times 10 to the minus 19th joules. All right, there is our stuff to deal with light. Now we go on to the electron. This is now getting into the part 2 of the dual wave particle nature. So now we start looking at the electron. And I think it's intuitive, or what we would think if you were just to ask someone to describe light as either a wave or particle, they would say wave. If you were to ask someone to describe an electron as either a wave or a particle, they would say particle. That's kind of what our brain identifies as what makes sense. But light has a dual wave particle nature. We've seen that with the photoelectric effect. And incidentally, so do electrons. Electrons have a dual wave particle nature too. So we start off with the one that's intuitive, the Bohr model of the electron cloud. It describes it as a particle, as does all of the other models, except for the last one we're going to look at, which is the quantum mechanical model. The electrons exist then in very specific energy levels orbiting around the nucleus, kind of like the idea here. We have the nucleus, electron cloud, electron cloud, electron cloud. We have electrons in here, 8 in here, and then 18 in the next one. And so that's the Bohr model. How does it answer that elements have specific emission spectrums? This is a really important part of the Bohr model. Now, a lot of the Bohr model issues prevent it from being widely usable, but this is one of them. This is a really important thing. So what we see is light coming from excited electrons falling back to lower electron levels produces a specific kind of light. Now we can cite them with electricity or fire or something like that. And they produce a very specific color of light. They produce this emission spectrum. And the spectrum then shows that the electrons are falling from a very specific electron shell to another specific electron shell. Because if they could fall anywhere or exist anywhere in the electron shell, in the electron cloud, then we would see a continuous spectrum, a rainbow pattern, as opposed to individual bright lights in that. So that's how it explains that they have different emission spectrums. And could it adequately explain the locations of the electron cloud? Nope. And this is just one of them. So this is just a simple yes or no question, and it is no. So what is an energy level? Energy level are these locations where electrons can exist. And so going back here, here's the first energy level, second energy level, third, and so on. And we start writing those out later with electron configurations. These are analogous to the rungs of a ladder. So on a rung on a ladder, as you go up this ladder, you cannot step in between the rungs, just like electrons can't exist in between electron shells. So that's one thing. Also, as you go up, you're increasing your potential energy. Same thing here as electrons go to subsequent electron shells, their energy also increases. All right. Emission spectra we already talked about. We'll relate it up here, so we'll skip that one. All right, for number 25, I'm going to draw you kind of a simple picture. So if we think about electron levels in terms of two-dimensional, easy-to-draw networks, we would see this. We have this right here. We have that idea here. And so this would be the first energy level, second energy level, third, and fourth. And we'll say that this is a hydrogen atom. So the electron starts off in the very first energy level. If you excite it, whether that's by shining light at it or electricity or fire or something like that, it can bounce up to a higher energy level. That requires energy. Now, this isn't going to stay there. It can't, because just like climbing a ladder, you're not going to stay at the top of the ladder. Eventually it has to fall down, and it does so immediately. So it falls back down to another energy shell. It does not have to be the shell it came from. It could be to the third or the second. And subsequent amounts of energy will be released based on where it falls from and to. And when it does this, I'm going to draw this way out here. It releases that energy. And it releases that energy in terms of a photon. Since we have this, energy is equal to Planck's constant times frequency, then that photon has a very specific frequency, and then it has a very specific wavelength, and from there it has a very specific color. And that's the emission spectra that we see. Now, if it falls within the visible spectrum, we can see it, and not all emission spectra do fall in the visible spectrum. All right, so let's do some calculations here. Consider the following levels of a hypothetical atom. So these are the different energy levels and their respective energies. See, as you go up, the energy increases. So there's that. All right. What is the wavelength of a photon needed to excite the electron from that to that? So all we do is take the last one minus the initial one. So E4 minus E1. And that gets us our energy. The difference there between the two, I have 14 times 10 to the minus 19th. And then if we want the wavelength, we have to go through that whole process I just showed up here. Kind of wish I didn't erase it. We have 14 times 10 to the minus 19th joules is equal to Planck's constant times frequency. Frequency is equal to 2.1 times 10 to the 15th. We go on to the next one. The speed of light is equal to wavelength times frequency. So we have the wavelength here is equal to 1.4 times 10 to the minus 7th meters, or 140 nanometers. So there you go. All right, B, what energy must a photon have in order to excite an electron from the second shell to the third shell? It's the exact same process as this part right here, only we stop there. It's just a state function. So we take 8E3 minus E2 gets us 5 times 10 to the minus 19th joules. Simple. All right. Let's do the last one with this group. I'm going to have to leave that. When an electron drops from E3 to E1, as the atom is said to go under emission. Calculate the wavelength. Now this one is a little bit weird here and has caused some students in the past to get a little flustered. So we're going to look at this here. E1 minus E3 gets us negative 10 times 10 to the negative 19th joules. And this thing right there really bothers some students. It says, well, it's a negative amount of joules. Incorrect statement. It's that we have 10 times 10 to the minus 19th joules being released. So if it's being released, any kind of calculation we do with it from now on in order to get wavelength, we don't need to use. We just get rid of that negative. So we go through that same process we did before. We use this here first. And we use this one next. I'm not going to go through all that. And we end up with a wavelength of 200 nanometers. That's your final answer. All right, so the Balmer series is a emission spectra of hydrogen. And if we look at the first line of it, so this is going to be the first color of it, it has a wavelength of this. I think that's going to be like the, boy, is that the red or the purple? I can't remember right now. That many nanometers. So we want to know the energy difference between those two lines. Well, we have this first, and we have this next. So it's the same process we've done before. It's just worded in a way that makes it seem weird, and it's not. So we're looking for the energy difference. This is the wavelength that's produced. Energy difference is going to be related to this here. So we end up with an answer of 3.03 times 10 to the minus 19th. So again, we convert this into meters, put it into the speed of light equation. Once we get a frequency, we plug it into our energy equation, and we get this. All right, now we get to use the new equation, and this is the change of energy related to electrons falling from different shells, and these different shells then don't have specific values like they did up here. Since they don't have specific values, we just have the number of the shell that they're falling from, and 2. We get to use our new equation, and the new equation is going to be these are squared, initial minus final, and R is the Rydberg constant. And the label on that guy is going to be joules. 2.18 times 10 to the minus 18th joules. So we have change in energy is equal to that Rydberg constant. Just like before, I'm going to use the constant value instead of actually writing out the numbers. 1 over 5 squared minus 1 over 3 squared. So 1 over 25 and 1 over 9. Change in E is equal to 1.55 times 10 to the minus 19th joules. Again, this is going to be a negative number, guys, and we ignore that negative because we're trying to figure out the wavelength. The wavelength is based on whatever energy is either given off or received. It doesn't matter the direction, just the value. So we can take the positive there, and then we plug it into here. Speed of light is equal to this guy here. Oh, I see. I went ahead and combined the equations for this one. So on my notes, it looks a little bit weird. So we have this guy here, and we have energy is equal to Planck's constant times frequency, and the speed of light is equal to wavelength times frequency. So this problem is actually very long. We have our joules. Plug this into the next equation, the photon equation, and then we get the frequency and plug it into the wavelength equation, and we end up with the wavelength equal to 4.86 times 10 to the minus 7th meters, or 486 nanometers. So there is our final answer. Our frequency answer, do I have that? I do not have that. I went through the entire substitution process before I did calculations. So this is the one that we need here is the, is it? Oh man, guys, I apologize. I mixed two problems together here when I'm looking at my key. I gotta go back and fix some of this for you. Sorry, you're probably just freaking out going, what's going on? So the answer is a little bit different. It's going to be the same process, and we end up with the wavelength of, instead, is equal to 1.28 times 10 to the minus 6th meters, or 1280 nanometers. That's the right answer for that one, guys. This is still the same, and the process was still the same. It's just that answer that's different. All right, now we can go on to question number 32, which is exactly the same as this, so I'm not going to go through the entire process. I'm just going to go ahead and write the answer down. And I'm going to leave that up there right now. I'm just going to put it here. The final answer is what we did before. 486 nanometers. There you go. Same process, no change, just different answer. Got a couple of the conceptual questions to go through quickly. De Broglie's answer to the question that could not adequately explain of why is the electron in the Bohr atom restricted to orbiting the nucleus at certain fixed distances has to do with the behavior like waves. So since electrons are not just particles, we can look at what they would be like if they were circling a nucleus in a wave-like pattern. And because of this wave-like pattern, it prevents this decay process. So in here, it talks about how particles would emit radiation and lose energy around the nucleus. So that's what a particle does. And since this doesn't happen, we said, well, if it's a standing wave, and a standing wave is a special kind of wave that will not cancel itself out with as long as it has a fixed orbit equal to the circumference of the energy shell, it will not cancel itself out as it goes around the nucleus. So that's an important piece there, and why we can show that the electrons are like waves. So there you go. Number 38. So de Broglie said that all objects had wave properties, wave characteristics, and so if that's true, we can look at a baseball and say, well, if we're throwing a baseball, why don't we see wave characteristics? Why isn't it going like a sine wave through the air? And that's because of the equation is based on the wavelength equals to the Planck's constant times the mass times velocity and Planck's constant is such a small number, 6.63 times 10 to the minus 34th, we have to have a super small mass before we start seeing a wavelength that is noticeable. So that's why we don't see them for anything else other than for subatomic particles. All right. Now we can do a couple problems related to this. Number 39, thermal neutrons are neutrons that move at speeds almost or to those of air molecules at room temperature. The neutrons most effective for initiating a chain reaction among these for 235 uranium. Calculate the wavelength associated with the beam of neutrons moving at 700 meters per second. So we have our wavelength. Is equal to Planck's constant divided by mass times the velocity. So we have h divided by 1.675 times 10 to the minus 27th times 700. This is important. In this equation, you need to have kilograms, you need to have meters per second. Once you have those, you can calculate, and it turns out to be 5.65 times 10 to the minus 10th meters, negative 10th meters, or 565 nanometers. Number 14 is the same thing, and this is the one I was thinking about, that we can accelerate these things almost to the speed of light. 3.0 times 10 to the 8th meters per second is the speed of light. So we can do this problem the exact same way. The mass is going to be this guy over here. And then we have the velocity here. Now, this is fixed on yours. It's not fixed here. This number 3 should be a multiplication sign. So we have that. So our wavelength is equal to 1.37 times 10 to the minus 15th meters, or 1.37 times 10 to the minus 6th nanometers. Now we can show de Broglie's equation in action with some object that's significantly larger than a subatomic particle with a ping pong ball. So let's look at number 42. This one is not as easy as the others, not because of this equation, because this equation is super easy. It's because this isn't in meters per second, and this isn't in kilograms. So we have to change those things. The mass of the ping pong ball is easy. That's 0.0025 kilograms. Now we have the miles per hour. So we start off with 35 miles. Gonna take some work. Per hour. Do 1.6. We're going to skip this. We're going to go 1,610 meters per 1 mile. Now we can focus on the time because miles goes away. We're left with meters per hour. That's our units. Now we have to get meters per second. So if we go through here, we have 1 hour is 60 minutes. And then 1 minute is 60 seconds. Cross out the things that cancel. Hour cancels, hour cancels. Minute cancels, minute cancels. We are left with then the label of meters per seconds. So that was kind of a blast from the past there to show you how to do this kind of factor label method to do some more complicated conversions. And we end up with a value there of 16. Multiply this by 16. We have a wavelength of 1.7 times 10 to the minus 30 second meters, or you can put this in as 1.7 times 10 to the minus 23rd nanometers. Ridiculously small wavelength. Can't see it, no possible way, so we're good there. All right. Learn objective 2, the quantum mechanical model. So with the quantum mechanical model, first of all, we look at the electrons in terms of their wave characteristics and less like they are as a particle. And because of this, though, we end up identifying these areas within the electron where it's probable that we see the electron. And that's called a wave function. And we'll talk more about that as we go through this. But understand that we have these specific orbitals where the electrons exist, and it's different than how these orbitals are described with the Bohr model. The Bohr model shows that shell. So if we look at that again, we have the Bohr model that looks like this, and electrons exist in the rings. That's not the image that we should have. The image we should have is more of like a cloud, and then we have the electrons having a probability of being located in a specific area. All right. Okay, so that's what this says here. Just gave you some big background. Let's look at some specific information. How does the concept of electron density describe position and the quantum mechanical position of an electron and the quantum mechanical treatment of an atom? And we use orbitals. These orbitals represent an area of electron probability. And we cannot know, so this is what's called the Heisenberg uncertainty principle. We cannot know an electron's momentum and location at the exact same time. So there's location, there's momentum. This is analogous to a photo finish at a race. So if you take a photo finish of someone crossing the finish line, you know exactly who won, but you don't know who is running faster at that point. So that's similar to what's going on here. The more you know about one, the less you know about the other. And the math that's involved here, we don't do. It gets really messy, and we involve calculus, so don't have to worry about that. All right, what is an atomic orbital? How is it different than an orbit? So this is what I was trying to describe earlier. An orbit is what Bohr calls them. And so this is a well-defined circular path the electron follows around the nucleus, where an orbital is a region in space where the electron has a probability of existing. So that's the big difference there, and that's the language difference, so orbit versus orbital. We have three different things that we use in order to describe electron configurations and how we write them. The first one is called the Aufbau principle. This says that electrons fill the electron level at the electron cloud in the very lowest possible energy level. So if we still think about it, even though it's not completely correct, if you still think about this in terms of a ladder, it's gonna fill the lowest rung first, and then the second one, then the third one, and so on. It's not going to jump to the fifth rung. Let's go to Hund's rule first. Hund's rule states that electrons are going to fill these atomic orbitals in a way that minimizes electrostatic repulsion. And so we're going to start looking at this here when we write these, but this is a review from general chemistry. When we write like a p orbital like this, the electrons separate before they have to pair. And we call this the empty bus seat rule. So if you imagine a set of strangers getting ready to get on a bus and have to sit together, for the most part, strangers are not going to share seats with somebody like this if there's an open seat for them to take. And so they spread out before they start pairing. The Pauli exclusion principle says that no two electrons can exist in the exact same orbital and have the same spin. Now, there is a more detailed definition of the Pauli exclusion principle than this. This is the one that we use because if we open that particular piece of information, that box of information, then we have to dig into it really, really deeply, and we can just change our language a little bit, and we end up with a discussion of spin. So when we draw those electrons, so here's an atomic orbital, one electron has to be spinning one way, the other electron has to be spinning the other way. We will not see so two electrons are spinning the same direction. All right. Now we can start doing our electron configurations. Now I do not have easy access to a periodic table on this to show you how this works. And so this is going to have to come from you guys' work and practice in class and just looking at the answers here for verification. So here are the answers for why each of these is wrong. 78, here are the number of unpaired electrons. Now I can show you one of these so you can see what that looks like. Boron has the electron configuration of this, 1s, 1 or 2, 2s, 2 and 2p, 1. It has that one unpaired electron. So all of these give the number of unpaired electrons that each one has. All right, I am maybe going to do one of these, guys, maybe one or two, so you can see them. But again, this is practice in class, and this is really, really easy stuff once you get the hang of it. And so I don't want to take the time, because to go all through all of these, it would take about 20 minutes, and that's a little excessive. So let's do vanadium. Ooh, I switched to red. Let's get back to blue. Vanadium has 23 electrons in it, and we end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And that is the electron configuration for vanadium. There are several different ways that we can, there are two different ways that I use in order to teach electron configurations. One is called the diagonal rule, which if you're with me, you may remember that. The other one is just by using the periodic table. I find one is easier to learn, that's the diagonal rule, and one is more useful, that's the periodic table. So I try to do both with the general chemistry students, but if you need a brush up, let me know and I can work on those with you. All right, same thing here, going to skip through those. Oh goodness, the photoelectron spectroscopy. This got added new to AP Chemistry a couple years ago in 2013, and I can't really describe to you how frustrated a lot of the AP Chemistry teachers are. It's not a hard subject to teach or to learn. It's just something that it seems kind of strange, like why are we putting it here? So in class, we will or would have talked specifically about what photoelectron spectroscopy is and why it's used and all that different stuff. And now we're just looking at the spectras and analyzing those. So the first question here, let's see if I can scoot this up just a little bit more. Okay, I cannot have both, so I'm going to do the work here and then show you the answers as I go. So it says, the first question says identify the element and write its electron configuration. I'm going to just identify the element, and we can do this by counting the number of shells in each one of these peaks. So this is going to be, or electrons in each one of these peaks. So this is going to be electron 1, electron 2, 3, 4, 5, and 6. So we have 2 electrons. Oop, we're on this side. No, this is the right side. Sometimes the units go backwards, guys, so be careful. This is going to be closest to the nucleus. The largest number is going to be closest to the nucleus. The smallest number is going to be farthest away from the nucleus. So we have 2 electrons here. That is going to be our 1s. We have 2 electrons here. That's going to be our 2s. There's 6 electrons there. We have 2 electrons there, and we have 1 electron there. So we end up with 1s2, 2s2, 2p6, 3s2, and 3p1. And I have silicon written down, but I think that's aluminum. 10, 13, yeah, 13 is equal to aluminum. My fault there. All right. Now let's double check there. 1, 2, 3, 4, 10, 12, 13. Yep, for sure that's aluminum. All right. The letter B, sketch what it would be if we had phosphorus on here instead of aluminum. So if we go through here, now since phosphorus has more electrons, more protons, we're going to shift this to a higher value because of the effective nuclear charge by the nucleus. So all this is going to be the same. This is the same. This one's the same. This one's the different one. Phosphorus ends up with our 3p3. So there is that last 3 electrons that we have. Okay. So there's that. Now we got to go through and talk about the next part. Number 2, how many peaks would you anticipate for copper ignoring any splitting within a sublevel? The relative intensity of peaks for chlorine is 2, 2, 5. So there it is. So this is our, well, it says 2, 2, 5. 2, 2, 5. This means it's 1s2, 2s2, 2p5. So that's simple. That's how we can see the peak differences. Now, in this case, we would see a total of 7 peaks because we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That's going to be our end of copper. So we have our ratio of 2 to 2 to 6 to 2 to 6 to 2 to 9, and I guess we could reduce these 1, 1, 3, 1, 3, 1. What would that be? Maybe we can't. Nope, I guess not. All right, never mind. All right, so there is the relative peak intensity for those. All right, number 3, a student makes the claim regarding magnesium and neon that since magnesium is isoelectronic with neon, meaning they have the exact same electron configurations, their spectra will be identical. And this is a false statement because of the number of protons that each one has. Magnesium has 12, neon has 10. We have a larger effective nuclear charge here. I guess we're going to be talking more about this in Chapter 8, but more protons, greater attraction to the electrons it has, so it's going to pull them more tightly. And so it'll be more difficult to remove these guys, especially towards the core electrons as we get closer to the nucleus, so it's going to have larger values than the neon would. All right, number 4. This one is way easier than it looks like. We have photons with this kind of energy, and the kinetic energy of the electron. The kinetic energy of the electrons that are ejected has this value here. So if this is the amount of energy used by the photons, then the binding energy is just the subtraction of those two different things. So how much energy was given, how much energy was released, so the binding energy is the difference between those. And that should be a capital N. There we go. Number 5. We have a portion of the photoelectron spectrum for phosphorus and sulfur. And we have these two things. This is actually a really hard problem, guys, so let's look at this carefully. First of all, I want to make sure we see this. This part right here, unimportant. These parts there, important. So we see the two different ones. Now, I wish there was a key over here. Let me see if I can figure this out real quick. The charge for sulfur is greater than phosphorus, but the binding energy is unexpectedly lower for sulfur. Justify. And so if we look at the electron configuration, we have 1s, 2s2, 2p6, 3s2, 3p, 1, 2, 3. That's going to be our phosphorus. And we have sulfur, which can have the exact same thing, only end in this. 3p, 1, 2, 3, 4. Now, since sulfur has more protons, we would expect it to have a greater binding energy. So the blue here is going to be our oh shoot, I can't tell right now. Yes, that's right. The sulfur is going to be the pink, phosphorus is going to be the blue. So we see that here. It's more difficult to remove the core electrons from sulfur than it is from phosphorus because of the core electrons and the extra protons that sulfur has. But if we look at the P block, we see that phosphorus is more easy to remove those electrons than it is from sulfur, which is backwards of how it should happen. So we have sulfur here with a much larger value, 1, 2, 3, 4, and we have phosphorus here with 1, 2, 3. I've been lower than sulfur. Oh, yeah, that's where, okay. Sorry guys, I just got myself confused. So this is a little bit lower than it is for here. And the reason it's lower, it's backwards of how it should be. The reason why it's lower is because of this configuration right here. It turns out that not only is a full shell makes it very unreactive and is a good thing for the electron configuration, but a half-filled electron configuration also is favorable. And so that's why it's a little bit higher for our sulfur than it is for our phosphorus. So there you go. Or excuse me, higher for our phosphorus than our sulfur. All right, we are almost done here. We have periodic table concepts, which these will go quickly. Number 5, identify these as metals, nonmetals, or metalloids. Look at the periodic table and make sure you know where these are. Compare the physical and chemical properties of metals and nonmetals. Metals are these things: shiny, malleable, ductile. Now, malleable and ductile are different. These are keywords that we need to know now. Malleable means that it can be hammered into thin sheets like aluminum foil. Ductile means it can be drawn out into thin wire like copper wire. Conducts heat and electricity. Some of them, many of them, react with acids to produce hydrogen gas. Nonmetals, essentially the opposite. Dull, brittle, not conductive. Carbon is, and that's super important, especially for the future use of like carbon nanotubes and things like that. They have high ionization energies and high electronegativities, and many of them are gases. One of them is a liquid. Now, number 7, draw a sketch. Okay, you're going to like this sketch here, guys. Here's my sketch. There's the periodic table. There's the diagonal. There's metals, there's metals, there's metalloids. There you go. Representative elements are going to be the S and P blocks on the periodic table. So we ignore the transition metals and the rare earth metals. So an example of this would be like, I don't know, phosphorus or sodium, something like that. You're given an element with these properties, either iodine or metal. So it's just, and this is key, a non-destructive way of telling whether or not it's a metal or iodine. And all you have to do is check its conductivity. Metals will conduct, iodine will not. valence electrons. All right, again, guys, this is straightforward stuff. The valence electrons here. What do I mean when they're isoelectronic? It means they have the same exact electron configuration. Without consulting the periodic table, write out the ground state electron configuration of this thing, and then identify the element or classify. It's going to be a nonmetal because of its electron configuration. Let's get that in here. Actually, we have 1s2, 2s2, 2p6, 3s2, 3p5, and we can tell it's a nonmetal because of this. It has 7 valence electrons, and those 7 valence electrons means it's going to be on the right side of the periodic table, and that it will be a nonmetal, and that means it's also, we can also even classify it as a halogen. So there's that. All right. Write the ground state electron configuration for 5 of those. Not going to happen. Let's look at, boy, yeah, I don't want to do any of these. You're just going to be adding and subtracting electrons. The biggest thing here, guys, is if you end up with something, the one that would have been nice to have on this list, I'm not sure why, maybe this problem isn't getting at this, but if we had something like vanadium, click through, and we can do vanadium again. It has 23 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And let's say then we had vanadium with a positive 3 charge. No, we're not do that. Positive 2 charge. Has 21 electrons. Those electrons come from the outermost energy shell first. And so we'd end up with electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. And actually, when we're doing it this way, if we did it noble gas, we could skip that, but we'd go 4s0, 3d1. There you go. Periodic trends. Guys, this is some of my favorite stuff here with periodic trends. I love it. It makes so much sense when you actually get the hang of it, and you can explain so many things with it. So please make sure that you focus on this and review the explanations and review the notes that we take on it. So we have the 4 different trends we're going to be looking at: atomic radius, ionic radius, then we also have electronegativity and ionization energy. And so we're going to start with atomic radius. That's the size of the atom. Now, the actual definition of it is that it's 1/2 the distance between 2 nuclei of 2 identical atoms bonded together. You know, for example, we have an oxygen atom bonded with an oxygen atom. Oh shoot, how much of this do I want to show you guys? Because we haven't studied how to draw bonding. So, well, we'll do it correctly. It has a double bond. It's 1/2 the distance from the nucleus to the other nucleus. And we do this because the electron cloud, by definition, is kind of cloud-like, and so you aren't able to easily identify the edge of it. So that's important there. So does it have a precise meaning? Not really, because of the fact that the electron cloud is an undefined region in space. How does it change it going across the periodic table? So if we were to draw a periodic table, so there's my awesome periodic table. It decreases going this way. So I'm going to draw it this way. It decreases going that way, so this is increases to the right, and it increases going down as well. So there's the periodic trend for atomic radius. And here is why. Why does it decrease going from left to right? And it has to do with what's called the effective nuclear charge. The effective nuclear charge is the pull the electrons feel from the nucleus. Yeah, that's it. The pull the electrons feel from the nucleus, the relative pull that they feel from the nucleus. So if we go across the periodic table, say from sodium to magnesium to aluminum, we're adding more protons. The nucleus is becoming more positive. At the same time, we're still adding electrons. So this is the counterintuitive part. You'd think if you're adding electrons, the electron shell would get bigger. But those electrons are going into the same electron shell here. And so since they're going into that same electron shell, the pull on those electrons is tighter, and so it shrinks. And so we end up with like sodium, magnesium, aluminum, and so on until we go down to the next row where we end up with potassium. Now potassium is quite a bit larger than sodium as we go down the periodic table, because each time we start a new row, we add a new electron shell. All right, click through here. Ionic radius. So we have anions and we have cations. Anions are always going to be larger than their neutral counterpart, and cations are always going to be smaller. And so this problem is the why. So why are anions larger than their neutral counterpart, and how come cations are smaller? And it has to do with that effective nuclear charge. If we add electrons to make it negative, that means that the protons of the nucleus are not going to be able to hold on to those electrons as tightly. Therefore, the radius expands. The opposite is true for cations. If we have less electrons and the same amount of protons, then the effective nuclear charge is greater and the radius shrinks. So let's look at this with an example. If we have oxygen that's neutral, we have 8 protons and 8 electrons. If we have oxygen with a -2 charge, we have 8 protons and 10 electrons. There's 2 more electrons here, which means that the effective nuclear charge by the nucleus is smaller. There's more electrons than there are protons, so the nucleus expands. The opposite would be true for something like magnesium. It has 10 protons, 10 electrons. Or magnesium with a +2 charge would be 10 protons and, oops, sorry, I messed it up. 12 and 12, we have 12 and 10. Less electrons there, so the nucleus has a greater pull on the remaining electrons, so it shrinks. All right, so which one is going to be the largest one? And this is actually just really redundant. It's always the one further down the nucleus or down the periodic table. I didn't really see that all of these problems are almost identically the same. Just repeating the same concept with different elements, but that's how it is. They're all further down than the other one, and so the one that's further down is always going to be larger. Okay. Why is the radius of sodium atom considerably larger than that of the lithium atom? It's the same reason that we talked about before. There's more electron shells, so it's a larger atom. Which of the 2 species is smaller? It's going to be the neutral if it's negative, or positive if it's the charged one. So here we have those 2 there. C, though, has 2 different atoms with the same charge. So it's going to be the one that is further up on the periodic table or further to the right. So we have our oxygen. Aluminum here is going to be, oh, that's a good one. So if it has a greater charge, it's going to be smaller because we have fewer electrons, so the nucleus is going to be pulling more tightly on them. Well, same thing here, magnesium, aluminum. Aluminum has more protons than magnesium does, so its effective nuclear charge is going to be higher, especially with the 10 electrons as opposed to the 2. And that's what we explained here, and we explained that here as well, talking about these up here. So we'll skip through that. Now we can get on to ionization energy. Ionization energy is the amount of energy required to remove a neutral or an electron from a neutral atom, or I guess if that's the first ionization energy, the second and third and subsequent ionization energies would be the amount of energy to be required to remove electrons from an ion. So we have that. We measure them with atoms in a gaseous state so that there aren't any other forces at work that we need to take into consideration, because the atoms are going to be very, very far away from each other. So we're dealing with that one specific atom and nothing else. The second ionization energy and third ionization energy and so on are always going to be larger than the subsequent one or the previous one, because we're taking it away from that charged atom. The number of protons are the same, so we have a greater effective nuclear charge. Remove electrons, greater effective nuclear charge. It holds on to those remaining electrons more tightly. Here's increase in ionization energy. So ionization energy increases going this way. Oops, didn't mean to do that. It increases going this direction and that direction. So the element with the highest ionization energy is going to be helium. The lowest is going to be cesium or francium, if we ever look at francium. So there we go, highest to lowest. So we just organize them in order according to that. All right, erase here. Number 55 is an excellent question. I love this question, and it really helps us identify how ionizations are important. There was a free response question on the exam a couple years ago directly related to this. So let's look at it carefully. So potassium has two ionization energies we're looking at, the first one and the second one. The first one, if we take an electron away from potassium, now it looks like, oops, argon. It is isoelectronic to argon. Now that is a noble gas. Noble gases have a full outer shell. So if we have a full outer shell, it's going to take a lot of energy to remove an electron from an atom that has a full outer shell. So that's why we see this huge jump from the first ionization energy to the second ionization energy. Where calcium has a 590 ionization energy for the first one. That's how much energy is removed for the second one. And then still larger, not just a significant jump. Now, incidentally, after calcium loses 2 electrons, it now looks like argon again. And so if we, is that right? Calcium. Yes, that's right. So we have argon again. So if we did the third ionization energy for that one, would be like, I don't know, 4,000 kilojoules. We see that huge jump again. So we can identify elements based on when this jump occurs, and that's pretty powerful. Going on to electronegativities. Electronegativity is how tightly an atom holds on to electrons it receives in chemical bonds. Now, since it's based on chemical bonds, since noble gases don't form chemical bonds without some kind of extra help from the observer, they don't have electronegativities. It does the exact same thing as ionization energy, only the noble gases don't have electronegativities. That's kind of a lie, guys. They do have, the ones down here do have electronegativities, but that's for reasons that we don't study in this class. All right, erase, click through. And we're done. Why does it do it this way? Why does electronegativity increase going across and up? And we discuss it in terms of its tendency to either get an electron from something else or lose an electron. So as we go from left to right, it has a greater tendency to gain an electron to have that full outer shell. Remember, it's always talking about pulling an electron that it gets in a chemical bond. So if it gets in a chemical bond, it's going to have a full outer shell. So the further right that we get, the more likely it is to pull an electron to get a full outer shell rather than lose or share one. And if we go from top to bottom, so why is it? Yeah, so why does the tendency decrease going down here? And that's because as we go down, the atom gets larger, it's more likely to lose an electron, and so it has a smaller electronegativity. So again, let's look at this just to have it in front of us again. increases going this way, increases going this way. This is saying that it increases going from left to right because of this reason, and then from top to bottom is asking this question: why is it decreasing going down? And it's greater tendency to lose electron because it has a larger atom. The larger atom means the electron is further away from the nucleus and more easily removed. All right, thanks guys.